All right, let's go over a few questions before we move on. The first question here says, a voltmeter is a device that is connected in parallel to the circuit between the points where the voltage is to be measured and has a very large internal resistance. It's connected in parallel in the circuit between the points where voltage is measured and has a very small internal resistance, is connected in series in the circuit between points where voltage is to be measured and has a large internal resistance, is connected in series in the circuit where between the points where the voltage is to be measured and has a very large internal resistance. None of the above. You have 1 minute. Please talk to a person next to you. Your time starts now. All right, 10 seconds, folks. All right, the correct answer here is obviously A. And the reason A is the correct answer is because you don't want any current flowing through the voltmeter, and hence you want the internal resistance of the voltmeter to be very large. So for example, if you remember, if this is a circuit and you're trying to measure the voltage between points A and B, you will put a voltmeter like this between these 2 points. This is a voltmeter here, and so this is connected in parallel to the part where you want to measure the voltage. So what you're trying to measure here, if there is a current I flowing here, what you're trying to measure is V of R, which is I times R. This is what you're trying to measure in this voltmeter. And the reason the internal resistance of the voltmeter should be very large is because this current I will actually split at this junction between the 2 parts, and we want the current in this part to be almost 0. And that will almost be 0 if the resistance is very large, right? In parallel, remember, larger is the resistance, smaller is the current. So then we want all of the current I to be passing through this, because we don't want to change the thing that we are measuring, which is V of R, which is I times R. And so the voltmeter should have very high resistance so that the current through that parallel path is almost 0. Any questions about this, folks? Anybody? Okay, let's look at another question. If the current in a circuit increases, the drift speed of the electron in the wire increases, decreases, remains the same, may increase or decrease, none of the above. You have 1 minute. Please talk to a person next to you. Let me explain this. What do you think should be the answer? Very good. The answer should be the drift speed increases, because if the current increases, that means you must have applied a higher potential difference, right? And that means the electrons are feeling a greater force, so they will be drifting faster, right? Does that make sense? So the answer should be A. So let's stop here, and now we are going to move on to magnetism. And in fact, I had already told you a little bit about magnetism. For example, we already discussed things about bar magnets, and what we said is that in a bar magnet, for example this, you have a north pole and a south pole, and it turns out that bar magnets show magnetism because of something called electron spin, right? And in a magnet, those spins on an average are pointing in a certain direction, and that is why this is showing the magnetic property. All right. In a regular, for example, chalk is not showing magnetic properties. It doesn't mean that the electrons in the chalk don't have any spin. They do, but the spins are all pointing in random direction, so there is no net magnetism in this material, right? But what we said is that if you cut this bar magnet into 2 parts, each part will actually itself become a magnet, right? North, south, north, south. If you cut it further, it will become 2 more magnets. In fact, at the level of electron, this thing will be a magnet too, right? Because electrons themselves have this thing called spin. So electrons themselves should be thought of as magnets. We also talked about the magnetic field lines of a bar magnet, and what do you remember from that? Anybody remember something about magnetic field lines of a bar magnet? Is it, First of all, a magnet should be thought of as a magnetic dipole, right? Because you cannot just have an isolated north pole or isolated south pole. North pole and south poles always come together. This is very different from what you've learned in electricity, where you can have just positive charges on something. Say for example, I could rub this chalk with something and create just positive charges on this, right, and the negative charges on that other thing with which I rubbed it. That's never possible for magnets. It will always have a north and a south together, right? So and it's not that there is anything wrong in just having a north pole or a south pole, just that we have never found it in our universe. So in the universe we always find north and south together, so a magnet will always be a magnetic dipole. But we also talked last time about what is the difference between a magnetic dipole and an electric dipole. Does anybody remember? So if I draw, say for example, this is a magnet, let's say this is the north pole and this is the south pole, and this is a plus charge and a minus charge. This is an electric dipole. And this is a magnet or a magnetic dipole. Do you remember anything that we discussed about what was the difference between the two cases in terms of what the magnetic field line and electric field lines will look like? Any thoughts, folks? Anybody? Okay, what would the electric field lines look like here? Tell me, anybody? Go ahead, please. Very good. They always, electric field lines always start at positive charges and they always end at negative charges. So here it will always be like this. You know, something like this. Of course, the electric field lines or magnetic field lines, neither of them can cross each other because the direction of electric field or the direction of magnetic field is given by the tangent to the line, and you cannot have two directions. If the lines start crossing, then there'll be a tangent here and there'll be a tangent there, and that's not possible. So lines will never cross. So this is the electric field lines for an electric dipole. What about here? Is this different? In what sense? Go ahead, please. Very good. The difference here is that outside the magnet, the magnetic field lines go from north pole towards south pole, but inside the magnet they go from south to north. So they form a closed loop. They go like this. You can see that things are going from south to north. You will never find that kind of thing from negative. Nothing is going from negative to positive. Everything is going from positive to negative here, right? On the other hand, here, look, outside it's going from north towards south, and inside it's going from south to north. So this is what the pattern would look like. So the difference is that the magnetic field lines form closed loops where there is no break. You follow the line, it keeps pointing like this, like this, like this, like this throughout, because inside it's pointing from south to north and outside it's pointing from north to south, and so it just forms a closed loop, right? That won't happen here, because here if you go like this, okay, it's pointing this way, this way, this way, this way, this way. Now, oh, now I have to go again this way, right? So it's not like you can keep following this arrow and you can get back to this. It won't happen there. So that's a difference. Now, I also told you last time that the Earth is a magnet, but a very weak magnet, right? So even if you bring a compass needle or something, if you bring a compass needle close to Earth, it will line up in the north-south direction, right? And it turns out that the geographic north of north is close to magnetic south and vice versa. Now, I also said last time that the physics of this bar magnet, the mathematics I should say, the mathematics of how this bar magnet works is much more complicated than we can do in this course. So we are going to focus not on this bar magnet. And the other thing is that bar magnets don't produce that strong of a magnetic field. So in all commercial applications, magnetic fields are produced by what? Go ahead, please. Yeah, current carrying wires. So in all of the commercial applications, the magnetic fields are produced by current carrying wires. So in the case of current, so it turns out that electron spins can produce magnetic field like here, but also moving charges can produce magnetic field like in current carrying wires. Their electrons are moving, right? So both of these mechanisms can give rise to magnetism. And remember that moving charges, to some extent it's under our control. If we apply a larger potential difference, there will be a larger current, right? And it turns out, as you will see over and over again in this course, that larger current would mean larger magnetic field. So current carrying wires produce a magnetic field, and that's the stuff that we are going to focus a lot on in this course. Also, what is current carrying wire? Isn't current carrying wire just moving charge? So one thing that you should immediately think about is, if current carrying wire is producing magnetic field, that means moving charges must also produce magnetic field, and that is true. So even if I had a single moving charge, that moving charge produces a magnetic field around it. Okay? But right now, here is what we are going to do. We are not going to talk about how a current carrying wire produces a magnetic field, etc. We will assume, okay, fine, so the magnetic field is there. Maybe we have used a bar magnet, maybe we have used a current carrying wire. There is some magnetic field, and this chapter is going to focus on what would be the forces on, say, moving charges in the magnetic field. What would be the force, say, on a current carrying wire in this external magnetic field, which is produced by something which we are not going to talk about in this chapter. It will be the next chapter. Is this clear to everybody what we are going to talk about right now? We will talk about forces on moving charges in a magnetic field and forces on current carrying wire in a magnetic field, without talking about what is producing this magnetic field that is exerting a force. So assume that it's some, just like we used to talk about we used to say, okay, so let's say that there is a uniform electric field. Maybe it's produced by parallel plate capacitors. What would be the motion of a charged particle in this electric field, right? That would be a fine question to ask. And we can say, okay, let's not worry about parallel plate capacitor. Let's just say there is an electric field, and how would the charge, what would happen to this charge if I place it in an electric field? We will ask the same kind of question about a moving charge in a magnetic field now, without talking about how this magnetic field is produced. That will be next chapter. Okay, so if that's the thing, one thing about magnetism, which I have emphasized several times already, is that magnetism requires you to be able to visualize things in 3 dimensions. No matter how crazy it sounds, this is the way our universe works. So it turns out that the magnetic forces are always perpendicular to the direction of a magnetic field. This sounds very absurd because, everything that you have learned so far, for example, gravitational force and gravitational field. If the gravitational field is pointing down, you know that the reason this eraser is actually tilting is because of this gravitational force pointing in the same direction as gravitational field, right? Similarly, if suppose that was a plate of a capacitor with positive charge, this with a negative charge, and the electric field was pointing down, and if I shoot a charge like this, will it also go like a parabola? It will. And in that case, again, is the force electric force in the direction of electric field? Yes, F is equal to QE. Just like for the gravitational case, F is equal to mg. So in those cases, forces and fields are in the same direction. Now you will see something very bizarre and weird. This is life, and this is actually the true thing, because physics is all about how real things work. What you will always see now is that the forces are perpendicular to the fields that produce those forces. So because of this, now we will have to learn a way to treat things in 3 dimensions. So let me, before we get into anything, let me teach you how we are going to show things that are actually pointing into the blackboard or out of the blackboard. In your case, that are pointing into your paper or out of your paper. Because if everything is in 3 dimension, we need to have a way to write those things. So think about it like this. If suppose I had an arrow like this, which had a pointy side, and then at the back of it I had like this, right? If this is an arrow, if suppose this arrow was pointed at you, if the arrow was pointed at you, don't you think you will be seeing just the tip of the arrow? So every time I draw tip like this, this means out of the board. So this is, in your case it will mean out of paper. Is everybody understanding? Okay, if this arrow was pointed into the board, what would you see? You would see this cross at the back. Do you see what I'm saying? So a cross, every time I draw a cross, this would mean into the board. So whenever, suppose I'm talking about a magnetic field that is pointing out of the board, I'm going to draw these dots. If I'm going to talk about a magnetic field that is pointing into the board, I'm going to draw cross. You know, I could be showing you a current carrying wire, and I could say, oh, the current carrying wire is represented like this. What would it mean? Which way is the current carrying wire carrying current? A long straight wire? Out of the board, right? If I show the current carrying wire like this, this would mean that the current carrying wire is carrying current into the board. Is everybody understanding that it's oriented that way? Okay, with this caveat in mind, let's try to learn something about forces on moving charges. So, and this is not a proof, this is how nature works. This is something that we have gotten from experiments. So this is an empirical fact that force on moving charge in a magnetic field let's give it a name, f sub b is given by q v cross b. What is this? What this says is that the magnetic force is the cross product of the velocity of the charged particle and the external magnetic field that is producing this force. By the way, often people use this language, they call it the magnetic Lorentz force, because Lorentz was the scientist who, you know, did important work in this area. So names are not so important, but oftentimes this is called Lorentz magnetic force. Okay, so what does it mean? You can already see this is a cross product, right? Does that immediately tell you that the force must be perpendicular to the velocity and the force must be perpendicular to the magnetic field? Shouldn't it? Do you remember from high school math that the cross product A cross B is always perpendicular to both A and B? Isn't that true? So if vector A is pointing this way, vector B is pointing this way, let's say, then I should think of a plane in which A and B lie, and I know for sure, even without doing anything, that A cross B will either be perpendicular to the plane this way or this way. And then I can use the right hand rule. Remember, A cross B can be found using right hand rule. What you do is you put all of your fingers in the direction of the first vector, curl it in the direction of the second vector, and the cross product will lie in the direction of the thumb, right? So the thing is, even before you use your right hand rule, what you remember from high school math is that to find the cross product, the first thing you have to know is that cross product should be perpendicular to each of these individual vectors. So let's try an example here, okay? Suppose, let's say that in this case we have a charged particle plus q whose velocity is like this in this direction, and the magnetic field here is pointing this way. The magnetic field is constant and the magnetic field is pointing this way, okay? I want to ask you at this moment, what would be the direction of force on this charged particle? What would be the direction of force? Yeah. Is everybody seeing that the way I have drawn it, the velocity vector is in the plane of the board, the magnetic field vector is in the plane of the board. Do you see that this is a plane? You know, so both of these vectors are in the plane of the board. I know immediately, because the force, magnetic force on this charged particle is going to be V cross B, is proportional to V cross B, it is perpendicular to V and perpendicular to B. That means the only way it can be perpendicular to both is if it is out of the page or into the page, right? Which of these it is? Now you use your right hand rule. Remember how to use right hand rule for cross product? What will we do? We put all of our fingers in the direction of the first vector, here V, of the right hand. It's important you use right hand. And then curl it. It's called the screw rule, right? Right hand screw rule. You put all of your fingers in the direction of the first vector, curl it in the direction of the second vector, and your thumb will point in the direction of the cross product or the direction in which the screw will move. So in this case, we had two choices, either out of the board or into the board for the force. We find that my thumb is pointing into the board, and hence the force is inward. So basically this magnetic force here is cross. Is everybody seeing? The direction of force is into the board, like this. I guess you have to try it yourself with your fingers, because you never learn right hand rule unless you try it yourself. So everybody should be trying this. What about the magnitude of this force? That's easy to find too. Remember the cross product? F sub B is given by the magnitude of this is Q, magnitude of Q, magnitude of V, magnitude of B times sine theta. Cross product, right? V cross B will be VB sine theta. So this is times sine theta, where theta is the angle between V and B. Let's say that theta was equal to 30 degrees. And let's say that the magnitude of the external magnetic field, B external, had a magnitude of, let's say, okay, before I talk about the magnitude of B, let me actually tell you what would be the unit of magnetic field. Is everybody comfortable with this, how to find the magnitude of a cross product? And there is a sine theta now? Okay, great. Can you tell me what should be the unit of magnetic field looking at this expression? Anybody? No fancy names. I want it in terms of things that we all understand, which is the unit of force, unit of charge, unit of velocity. What would be the unit of magnetic field? Anybody, folks? Go ahead. You were going to say something? So what would be the unit of magnetic field? Because we can see from there already that magnetic field is magnitude of force divided by magnitude of charge times magnitude of V. So what would be the unit? Anybody wants to tell me what is the SI unit of magnetic field? Huh? Go ahead, please. Very good. SI unit of B will be the unit of force divided by the unit of charge divided by the unit of velocity speed, because sine theta does not have a unit. Sine theta is just a number. It's just a number. So the thing is, unit of force we know is Newton, unit of charge is Coulomb, and unit of velocity is meter per second. So this is really Newton second per Coulomb meter. And it turns out we can again think of a shorter name for it, and it's called Tesla. The shorter name for this is Tesla, and we can write it with a symbol capital T. And again, Tesla was the name of a scientist. Bless you. So Tesla, 1 Tesla is what? 1 Newton second per Coulomb meter. Right? That's what it is. All right. So now let's try to do just a simple problem here. Suppose that this positive charge Q was 10 to the power minus 6 Coulomb. Let's say that the magnetic field was 10 to the power minus 4 Tesla. And let's say that the velocity of the charged particle at a particular moment was 2 meters per second. Do you think, and let's say that the angle between the velocity vector and the magnetic field was 30 degrees. We have already said that the direction of the force in this case, V cross B, will be into the blackboard, and that is a cross. What would be the magnitude in this case? Can we use this to find the magnitude? Yeah, all we have to do is multiply Q with V and times sine 30, and that would be the answer. So you can see over there that the magnetic force will turn out to be Q VB times sine theta, which is 10 to the power minus 6 Coulomb, times V is 2 meters per second, times B is 10 power minus 4 Tesla, times sine theta, which is sine 30 degrees. And this will be equal to 2 times 10 power minus 10. And sine 30 is a half, by the way. So this is basically 1 times 10 power minus 10. And what should be the unit of force if everything else is in SI unit? Newton. So I did not write the units in the intermediate stage, but I know the unit will be Newton if I have written everything else in SI units like I did here. Any questions about this, folks? Anybody? Okay, then I want you to talk to a person next to you and answer this question here. Suppose the magnetic field this time was pointing into the board. So magnetic field is like this. This is the B external, which is produced by something pointing into the board. It's uniform. And suppose I launch a positive charge plus Q with some velocity V in this direction. Which way will it feel the force? Is everybody clear? Direction of velocity vector is like this, magnetic field is like that. The question is, what is the direction of FB? Everybody should talk to a person next to you. You have 1 minute, I'm going to catch one person. Please. Sorry? Please. Okay, first of all, are you a lefty? No, you're fine. Okay. You have to use your right hand, right? So the thing is, you have to ask me after the class, but let me go with the whole class. Just stay back at the end of the class and I'll help you. All right, anybody has any thoughts on what should be the direction of the force? Up? How many people think it's up? Okay, one thing is that we already, again, using the right hand rule, you remember force is, this is Q, V cross B. So we already know that the force must be perpendicular to the velocity vector and the external magnetic field. In this case, the velocity vector is like this, magnetic field is like this. What directions are perpendicular to both of these? It can either be up or down, right? So the force can either be up or down. Does everybody see that those are the only choices we have? Because those are the only two directions that are perpendicular to velocity and to the magnetic field, which is pointing in, right? Now the question is which of these it is. In order to find that, use your right hand rule, which says put your fingers in the direction of velocity, the first vector, and curl it in the direction of the second vector. In this case, the second vector is the magnetic field, which is pointing in the board, into the board. So you can see when I do V cross B, my thumb is pointing up. And that means that is the direction of force. This is wrong. That was right. Right? Is everybody seeing that the force is up? Any questions about this? Okay. What do you think will happen if this charge is negative? If the charge is negative, notice that here you will have a minus sign. So for example, suppose this was not plus E, but this was minus Q here, not plus Q, but minus Q. In this case, you can see that FB will be whatever is V cross B times a minus Q, right? So it will be opposite of the direction that is given by V cross B. So for a negative charge, the force will be like this. Is that making sense? For a negative charge, first you do V cross B and then realize that Q is negative, and that means the direction of the force is negative of V cross B. Any questions about this, folks? Everybody is clear on how to find the force on a charged particle in an external magnetic field? Okay, so now let's talk about an important application of this concept in making something that is called a velocity selector, where we are going to use both electric field and magnetic field. Oh, by the way, before we make velocity selector, let me ask you another question, because this is a very good one. What happens if I actually place this charge in this magnetic field and it's sitting at rest right here? What is the force on it? So this charge has a velocity 0. What is the magnetic force on a charged particle which is sitting at rest in this magnetic field? Any thoughts, folks? It's 0, right? Do you see, if the velocity is 0, the force is 0. This is another very bizarre thing. So if this charged particle, if you have a charge, right, suppose you rub this thing with something and you produce some charge and you just held it constant, without any motion over here, does this charged particle even know that it's close to a magnet? No. It's feeling absolutely no force. It's oblivious of the presence of magnetic field, any magnetic field produced by anything. So charged particles do not feel any magnetic field if they are at rest. And so only moving, and you can kind of understand it, because only charges that move, only moving charges produce magnetic field. Only a magnet, something that produces a magnetic field, will feel the effect of other magnetic field, right? Magnets will attract or repel other magnets. So only if a moving charge is a magnet, not a static charge, then obviously only a moving charge can feel the effect of another external magnetic field. Does that make sense? So charges at rest don't feel any force. The other thing is, what about this case? Suppose this charge did have a velocity, but the velocity of this charge was also into the board. So this is the external magnetic field is across, and the velocity is across also. I want all of you to talk to a person next to you and think about which way would be the force on this charged particle if the magnetic field is pointing into the board and the velocity vector is also pointing into the board. Everybody, talk to a person. All right, any thoughts from anybody over there? Go ahead, please. Very good, because if you think about the magnitude of this force, you can see magnitude of this force is Q V B times sine theta. But if theta is equal to 0 degrees, that means the velocity and magnetic field point in the same direction. Sine of 0 degrees is 0. Similarly, what happens if the charged particle was actually moving out of the board? If it was moving out of the board and magnetic field was into the board, the angle between the two is 180 degrees, right? And if theta is equal to 180 degrees, sine of 180 degrees is also 0. So there is no force on the charged particle. So the charged particle is oblivious of the presence of magnetic field, no matter how strong the magnetic field is in which you have put it, so long as it's at rest, or it's moving in a direction parallel or anti-parallel to the magnetic field. It only feels a force when it is at some other angle, right? And this is very bizarre again, but this is how nature works. This is different from what you learned in the case of electric field, because in electric case, the electric force on a charged particle will be F is equal to QE. It only depends upon the magnitude of the charge, Q, and the direction of electric field and magnitude of electric field, QE. It doesn't say it depends upon the velocity or anything. So electric force does not depend upon the velocity, but magnetic force does. Does that make sense, folks? Okay. So now let's talk about the application that I was telling you about, which is a situation in which you have both electric and magnetic force on a charged particle. So here is what we want to do. what we have is a whole bunch of charges that are all moving at different speeds. You know, so we may have, for example, electrons or positive charges, protons, or whatever, some ions. They're all moving at different speeds. And suppose for some application, you know, some research that you were doing or some device that you were making, you only needed to have these charged particles. You needed to select the charged particles that are moving at one particular velocity. That is it. So now the question is, how do you get rid of all the other ones that are moving at different speeds, right? Do you see the idea? You want to select out, filter out all the charged particles that are moving with the exact same velocity. Throw out all the rest. Here is a method for doing that. So this is called velocity selector. And this method involves charged particle in both electric and magnetic field. And these electric and magnetic fields are going to be crossed. Crossed means they are going to be perpendicular to each other. So for example, let's say that the electric field was being produced by, let's say, parallel plate capacitor. So here is a positive plate and here's a negative plate. Which way is the electric field pointing, folks? Electric field always points from positive towards negative. So this is the direction of electric field, if you remember from chapter 1. Okay, so the thing is, if I launch a charged particle, let's say this charged particle is positive and it's launched with some velocity v, like this. This is the positive x direction, this is the y direction. So the charged particle is launched in the positive x direction. Which way will it feel a force due to this electric field? Down, right? Remember? F of E is equal to Q times E. Isn't this charged particle going to feel a force due to the electric field which is acting down? In the direction of force is in the direction of electric field. What will happen due to that force? The charged particle will? Which way will it move? If I ask you to show me the trajectory, what would you say? It will go, what will be the trajectory? A parabola, right. This is just like gravitational field. See, the gravitational field is pointing down. If I launch this mass in this gravitational field, you can see it's feeling the force down, which changes the velocity slowly, and it moves in a parabola. Similarly, this charged particle, when it is launched in the thing like this, it will move like this, right? Isn't that true? But the thing is, what we want to do, and these particles are going with a whole bunch of velocity. What we want to do is we want to be able to filter out a particular velocity over here. So we want all the other velocities to kind of, you know, go in these directions by tilting, but we want one velocity to be filtered out. What should we do? One way to do this would be to put this also in a magnetic field. So put this whole parallel plate capacitor in a magnetic field that is pointing into the board. So this is B external. So I have somehow put this whole thing between the plates of a capacitor and also in some external magnetic field that is pointing into the board. What will that do? That magnetic field, will it produce a force on this charged particle? Yes, and in fact I know the force will be this. F of B is equal to QV cross P. Which way will that force be? Let's do it with our hand. So first, again, look, if the velocity is like this at this moment and the magnetic field is pointing in, then V cross B, do you see the force is pointing up? So the magnetic force is pointing up. Do you see the magnetic force and electric force oppose each other? What we want is just for that velocity that we want out here. You know, because there are lots of velocities that are being inputted, you know, V1, V2, V3, V4, but we want just the one V to go out all the rest we don't care if it tilts this way or that way, because maybe the magnetic force is stronger than the electric force, but there's one for which we want the net force to be 0, right? So the one that we want to select, for the velocity we want to select, do you see, using this axis, this coordinate system, you know, if my f net equal to 0, it means that f's of b, which is in the positive y direction, minus f's of e should be equal to 0, right? The magnitude of the two. What does it mean? This means that f's of b should be equal to f's of e, magnitude. Isn't that true? Okay, what is the magnitude of f's of b? It's q v b times sine theta. What is sine theta in this case? Notice that the velocity and the magnetic field are perpendicular to each other. Isn't that true? So the angle between the two is 90 degrees. So this is sine 90. And this should be equal to q's of e, which is f's of e, which is q times e. E is the magnitude of electric field there. This q and this q get cancelled. Sine 90 degree is 1. So what we get then is Vb is equal to E, or the velocity should be equal to E divided by B. Is that making sense, folks? So the thing is, we can actually choose this particular velocity, and this would mean, how can we choose the velocity? I know that this is the velocity I want. What I'll do is I'll adjust my electric field and magnetic field that I'm applying in such a way that the ratio of the two is equal to the velocity. And if I do that, is there any net force on that charged particle? There isn't, right? So that charged particle will just keep singing la 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 la. It's totally undeviated, and it'll just go across. On the other hand, anything that is moving slower than that, anything, all the particles with speeds that are slower than that, which force will be dominant there, electric or magnetic? Electric, because you can see magnetic force actually depends upon V. So anything that is moving slower than that will have QE be greater than QV cross B, right? So those ones will actually eventually start tilting, and they'll go and hit this plate, right? Anything for which V is greater than this velocity, that corresponded to E over B, for those cases the magnetic force is greater than electric force, so those particles will slowly tilt this way, and they'll kind of eventually divert in these directions. So the one that will catch in our collector will be all the ones that are going, that have velocity equal to E divided by B, and this is the principle of velocity selector, right? So if, suppose for example, if we wanted V to be, suppose we wanted V to be say 3 meters per second, right? And suppose the electric field that we are applying is, let's say that the electric field that we are applying is 9 volts. You can see what should be the magnetic field? Huh? Do you see this should be equal to 3 Tesla? Sorry, this is not volts, but 9 Newton per Coulomb. Sorry, that is not voltage, that's the electric field. So let's say that the electric field was 9 Newton per Coulomb, then the magnetic field will have to be, the magnetic field will have to be 3 Tesla, because E over B, 9 Newton per Coulomb divided by 3 Tesla should be equal to 3 meters per second, right? I want all of you to convince yourself that the units work out right. That means Newton per Coulomb divided by Tesla should be meters per second. It better be. Is everybody understanding this? Any questions about this, folks? Anybody? Okay, then the next thing that we are going to talk about will be what should be the trajectory of a charged particle that is launched only in a magnetic field perpendicular to the magnetic field. So let's now talk about trajectory of a okay, but before we talk about trajectory, let me actually show you this experiment. So here is okay, so here is the, if you look here, do you see a blue beam there? That is actually a beam of electrons. There is a cathode here, and that cathode is spewing out these electrons that you see as a straight beam. Now, what do you think will happen? Here is a magnet, right? I'm going to bring this magnet close to this, and let's already predict what should happen. So suppose I'm bringing this north, this is the North Pole, right? Do you remember magnetic field lines go out of the North Pole, right? So if I bring the North Pole, that means like this from here, that means the magnetic field will be pointing that way towards the board, into the board. So if the magnetic field is pointing into the board, which way should be the force on this? Can you do it? So velocity of this electron is that way, v cross b. Do you see if it was positive charge, the force would be up, right? But is this positive charge or is this electron? This is electron, so the force should be down. Let's see if that is the case or not. So I'm bringing the North Pole, right? Watch. So the electron should deviate downward. Do you see the electron is tilting down? Huh? Can't see it? Okay. See, I'm bringing the North Pole, which means the magnetic field is pointing towards the board. It's crosses. Right? Okay, what do you think will happen if we bring the South Pole close? The opposite, right? Because the magnetic field lines go into the South Pole. So when I bring the South Pole in, the magnetic field is pointing towards you. These are dots. So let's see. Do you see? So exactly what you would predict. All right, so this is exactly consistent with right-hand rule. So we are basically learning how things work in nature. Now the next thing that we are going to talk about will be the trajectory of this charged particle in a magnetic field. Okay, so before we actually move on, I first want to show you the demonstration, and then we'll do the theory. So it will be in the other order. So let me show you. There is a cathode here that is giving out electrons, all right? And these coils that you see here, this is called Helmholtz coil, and it's producing a very strong but uniform magnetic field at the place where the charged particle is. Oh, here, there it comes. Hey, look at that. So that's the electron beam. That's the electron. And this coil that I'm showing you, this coil is current carrying coil, which is producing a very uniform magnetic field in this region, which is pointing in. Again, it's pointing into the board. What you see is that the charged particles are moving in a circle. Now what I'm going to do is I'm going to change the speed of the electrons that are coming out of the cathode ray, cathode by actually changing the, I'm going to change the speed by changing the voltage that I'm applying to the cathode. You see, if I apply a larger voltage, will it mean that the electrons will come out at a larger speed? Yeah, if the potential energy is higher, then the kinetic energy with which the electrons will come out will be larger. If the potential energy is lower, the kinetic energy will be lower. So you can see that if I change the voltage that I apply, I'm changing the radius of the circle in which the electrons are moving, right? Similarly, let's try and see what happens if I change the magnetic field itself. Hey, what I'm doing now is I'm changing the current in these coils, and if I change the current in this coil, I'm changing the magnetic field, and you can see when I change the magnetic field, it actually affects the radius of the circle. Do you see that? So there are several things that we have already understood and learned from here. One thing is that charged particles that are launched perpendicular to the magnetic field will move in a circle. The other thing we saw is that the radius of this circle will be affected by the speed with which the charged particles move, and it will be affected by the magnetic field that you're applying. Let's now see in theory if we can figure out exactly how to work this out. And it will not be very difficult at all. So first, let's first let's try to figure out, convince ourselves, yes, it's going to be a circle. The trajectory of this charged particle is going to be a circle. Let's figure it out. Okay, so let's assume that the magnetic field is produced by something, say the Helmholtz coil, for example, and it's crosses. That means it's pointing into the board. Okay, instead of considering electrons, let's right now choose positive charge. For electrons, the direction will be just the opposite, and I'll show you what it will be for electron. But let's say that I had a positive charge plus Q, that I launched with some speed v. Notice that v is perpendicular to the magnetic field, to the crosses. And I want to know what will be the subsequent motion of this. What would be the trajectory of this particle, right? What would the path of this particle look like? We do this thing, F is equal to V, Q, V cross B. Let's try to do it with the right hand. So V is like this, B is like this. Do you see that the force is pointing down? Is everybody seeing that magnetic force on this charged particle is down? Q, so V cross B. Sorry, thank you. V cross B, that means thumb is pointing up. Thank you, you guys are paying attention. That means what will happen is that this charge will, tilt a little bit that way. Do you see that? Okay, now that it has tilted this way, it's moving in this direction. This is the new direction of velocity. Now, which way will the force be at that moment? Let's say at this moment. Again, we can do the same thing. V cross B. Magnetic field is still into the board, right? This time we know, again, the force will be either perpendicular to the velocity this way or perpendicular to the velocity this way. Which of these is it? Use your right hand rule, V cross B. Do you see the thumb is pointing that way? So that means it's not this one, it's that one. That's the direction of the force, F sub B. So what will that force do? The force is this way, the velocity is this way. Will it tilt the velocity further like this? Wouldn't it? Yes. So the thing is, so the particle moves a little bit further and it tilts a little bit more. Let's say that now the particle is here. Now at this moment the velocity is tangent to the path this way. The magnetic field is still pointing into the board. Which way will be the force? V cross B. I know that the force will be either this way perpendicular to the velocity or this way perpendicular to the velocity, because those are the only two directions that are perpendicular to the velocity and to the magnetic field which is pointing into the board, right? Which of these is it? V cross B. You see that screw is going this way, that means the force is like this. So this is the direction of force, this is the direction of velocity. Will it tilt the particle a little bit further? Won't it? So you can see now, by now hopefully you have gotten the idea that this particle, that is launched in this magnetic field, which is uniform everywhere, keeps tilting. And in fact at this point now I can again say, oh, the velocity is tangent to the path like this, magnetic field is still pointing in, V cross B. Do you see the force is now like this? So that will tilt the particle a little bit further. So basically what we are seeing is that particle keeps getting tilted further and further, and what it happens is it starts moving in a circle. Have you ever seen instances where force is perpendicular to velocity all the time? Because we are saying, notice the magnetic force is always perpendicular to the velocity and it's always perpendicular to the magnetic field. Have you seen cases where force is always perpendicular to velocity in physics 1? What was that situation? You've seen it. Go ahead, please. Uniform circular motion. Whenever a charged particle moves at a constant speed in a circle, is there a net force required to keep the particle moving in a circle? Yes, there is a net force required, but we don't want the speed of the particle to change when it's moving at constant speed. That means the force should be perpendicular to the velocity, so that the force does not change the magnitude of velocity, it changes its direction. Because remember, you can have acceleration in two ways. Acceleration could be because the velocity's magnitude is changing, that means that something is going faster or slower, or it could be going at a constant speed, but if its direction is changing, That's change in velocity too, because velocity is a vector. If you change its direction, yeah, velocity is changing. And that's exactly what's happening here. This particle will be moving in a circle at constant speed. Its speed is not changing. Then what is this magnetic force doing? Magnetic force doesn't seem to be changing the direction, the magnitude of velocity. It's changing the direction of velocity. So this magnetic force is causing what is called a centripetal acceleration, right? Acceleration that is perpendicular to the velocity. Because wouldn't the acceleration be in the same direction as the net force? Would you expect F to be, net force to be in the same direction as acceleration? Which law tells you that? Again from physics 1. Which law says that the force on this charged particle, the net force on this charged particle, we are saying the magnetic force is always pointing towards the center of the circle. This is the direction of F sub B here. When the particle will be here, it will be towards the circle like this. When the particle is here, it's towards the circle like this. Always it seems to be the magnetic force is towards the circle. I'm saying, well, if the magnetic force is the net force and it's towards the circle, center of the circle, shouldn't the acceleration also be towards the center of the circle? Because net force and acceleration are in the same direction. Which law of physics tells you that? One of the most fundamental laws that you should be able to say in your dreams. Go ahead. Newton's second law, very good. It says net force is equal to mass times acceleration, right? And mass is a scalar. That means net force and acceleration point in the same direction. So let me just make this picture a little bit bigger so that you can see it a little better. So what we are saying is that this is the B external, and we are saying if you launch a positive charge perpendicular to this magnetic field, it will start moving in a circle such that at every point the magnetic force points towards the center of the circle, etc. And that is also the direction of the centripetal acceleration, the net acceleration in this case, which is caused by this force, right? Is everybody clear on this? What is the velocity? The velocity at every point of this charged particle is tangent to the path. So over here it will be tangent like this, 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 here it's like this, etc. Just like the way we did it over there, I just blew it up, made it bigger. Now from Newton's second law, we already said F net is mass times acceleration. In this case, we are talking about centripetal acceleration. What is the net force here? It's the magnetic force, right? And we already know that the magnetic force is QVB sine theta. So let's try to plug this in. So the net force is the magnetic force on the charged particle because it's in the magnetic field, which is pointing into the board. So F net is Q V, let's just worry about the magnitude right now, QVB times sine theta. What is sine theta here? It's sine 90 because of the fact that, do you see that the velocity and the magnetic field, which is pointing in the board, into the board, are perpendicular to each other at every point? The velocity vector here and the magnetic field, which is pointing in, are always perpendicular. So by construct, here we have sine 90, which is 1. And what is mass times centripetal acceleration? Does anybody remember how the centripetal acceleration depends on the speed of the charged particle and the radius of the circle? Yeah, it was v square over r, right? So if the radius of, so centripetal acceleration can be written as v square, the speed square, divided by the radius, right? One of the v's get cancelled. So what we are left with, let's try to figure out the radius of the circle here, okay? So one of the v's gets cancelled. So what we get is r is equal to mv over qb. So this is the radius of the circle, isn't it? I just rearranged the equation there. I'm just rearranging things. This is just 1, so this goes away. One of the v's gets cancelled. I took this r to the top, brought all this stuff down, and this is what I get. Now here is the thing. Notice the radius dependence on different things. So when the mass of the particle is more, the radius will be more. Velocity is more, radius is more. Charged particle has a higher charge, higher magnitude charge, radius will be less. Higher is the magnetic field, radius will be smaller. So larger magnetic field will tilt it more, but larger mass means it's harder to tilt. You can see. So the radius will be larger in those cases. Does that make sense? That larger mass and larger velocity means higher radius, larger charge, larger magnetic field, smaller radius. Any questions about this? Okay. What if I ask you, how long does this particle take to make one lap? By the way, can I also find the speed of this charged particle in terms of other things? So the point is, there are many things you can measure. Another thing would be, we can find v. You can see v will be equal to r q b divided by m, right? Do you see that? I mean, if you know, for example, that the particles that you're bombarding is electron, do you know the charge of the electron or not? You do. Do you know the mass of the electron? Yes, you do. Do you know the magnetic field? Yes, maybe you do because you have applied the magnetic field, or maybe you don't. I mean, the thing is, if you do know the magnetic field, if you can measure the radius of the circle, you can find the speed. By the way, if this particle was electron, what would be the only thing that would change? The only thing that would change for an electron would be that instead of this particle tilting this way, it will tilt this way. That will be the only difference, otherwise it's the same exact thing. The only difference is that this Q is negative, so the force is opposite to what V cross V predicts. So instead of the particle moving counterclockwise, in this case it will start moving clockwise. Otherwise it's exactly the same. Does that make sense? Okay. So suppose I ask you this question. Suppose I ask you, how long does it take to make one lap? Can you figure it out? Please talk to a person next to you and tell me how you would figure out the time taken to make one lap. Is everybody understanding the question? So the question is, all right, somebody from the second row here. Anybody from the second row, how would I find the period? That means the time taken to make one lap. Go ahead, please.
2 pi r divided by velocity.
Very good. Because if the charged particle is moving in a circle at constant speed, which is what we are saying, this magnetic field is only changing the direction of velocity, but the speed is staying constant. The period should be basically the circumference divided by the speed. So what she pointed out is absolutely correct. This would be 2 pi r divided by the speed v. And look at the speed v here. This is 2 pi, and speed can be written 2 pi r, and v can be written as r times q times b divided by m. So if it's divided by m, it goes to the top. Look at this. R and r get cancelled. And what I end up with here is that the period is 2 pi m over QB. Right? So if I gave you how much is the charge, how much is the mass, and how much is the magnetic field, you should be able to tell me what is the period. Notice something very bizarre about this result. Is there something very strange about it? Huh? It doesn't depend upon something that you might have expected it to depend upon. What does it not depend upon? Very good. It doesn't seem to depend upon the radius of the circle. Whether the radius is large or whether the radius is small, doesn't matter. The period is independent of how large the radius is. How can that be? Can anybody explain how it can be that the radius of the circle does not factor in determining how long it takes to make one lap? Just imagine yourself. Suppose you and your friend are in two different tracks, on a track, and running in circles. And suppose you were in a farther circle and your friend was in the inner circle. Both of you were moving at a constant velocity. How is it possible that both of you make laps in exactly the same time? Period doesn't seem to depend upon the radius. Go ahead, please.
The person in the larger radius is moving faster.
Very good. The person who is actually moving in the larger track is moving faster. In fact, we can see that from here. Radius is proportional to velocity. Larger is the radius, larger is the velocity. It goes as proportional to velocity. And that is the reason why how long it takes to make one lap is independent of velocity or radius. Right? So your friend and you could possibly make the same laps in the same amount of time, even though your track was smaller, because you could be moving slower than your friend who is moving in the larger track, right? And that's exactly what's happening here. Radius is proportional to velocity, so period is independent of radius in this case. Note, can we also find the time, the frequency, what is called frequency, which is 1 over period. That means how many cycles do you make in 1 second? So if you remember, frequency means number of laps per second, and we are going to use the symbol F for it. That is defined as 1 over t, right? Do you remember that from circular motion in physics 1? If that's the case, you can see the frequency. If it's 1 over period, it'll be QB divided by 2 pi m. Oftentimes we also define this thing called angular frequency. Does anybody remember how angular frequency and frequency are related? Good. Angular frequency omega is really 2 pi times f. So looking at this, angular frequency will just be QB divided by m. Right? Have you heard about particle accelerators? Can you tell me one place where particle accelerators are? Huh? Britain? There is a place close to it. I mean, in Switzerland, there is a place called CERN. They have huge particle accelerators. Also, there used to be particle accelerators in Fermilab, in Chicago, close to Chicago. So the thing is that particle accelerator is pretty much shutting down now. But what do these particle accelerators do? In particle accelerators, scientists are doing experiments where they're trying to accelerate particles, like for example electrons or protons, to extremely high speed, close to speed of light, for example, very, very high speed, because they want to see what happens at extremely high speeds. Because now we know, using these particle physics experiments, for example, that protons are themselves not fundamental particles. They are made of quarks, 3 quarks, right? Same with neutron. How do we find it out? We find this out by these particle physics experiments in which you bombard these particles at extremely high speed on each other, and you see how they interact with each other, right? What comes out, which way do the particles go? And based upon theory, people can actually interpret which theory is correct, which theory is not correct, and that will say how the interactions go. and what are the constituents of these fundamental what particles are fundamental and what particles are not. For example, we have never been able to break an electron. So and on the energy scales that we can actually go, we know that electrons are fundamental particles that cannot be broken apart. On the other hand, protons and neutrons are not fundamental. They can be broken into 3 quarks each, right? Up and down quarks. So why am I mentioning particle physics experiments? Because it turns out when you are trying to accelerate the electrons to higher and higher speed, first of all, what is going to do this acceleration? Will magnetic field make the electron move faster and faster? No. We just said magnetic field is magnetic force is perpendicular to velocity. The magnetic force is not going to make the particles move faster. It will make it move at a constant speed. Which force is going to make a particle move faster and faster for a charged particle? So suppose you had to build a particle accelerator, what would you think about? How would you make a charged particle move faster and faster? By applying an electric field? Yeah, F is equal to QE, right? So you apply a force, and if there is a net force, then the particle will have an acceleration. So that means if you started an electron from rest and you applied an electric field, the particle will move, right? And start accelerating. Acceleration again will be F is equal to QE, which will be equal to MA. So you can figure out what A should be. Now, these particles need to be accelerated for a long period of time before they can go to speed of light. Now, what do you want to send this electron from, say, Pittsburgh to India or something? You want to. So the thing is, you need to be able to apply this electric field over a long period of time to make it move faster and faster and faster and faster. So what would be a good way to accelerate the electrons? Because the thing is, it will require a lot of distance traveling before the particles can come to, because you can keep the acceleration to certain value, but then the speed keeps increasing, and it takes a long time, right? But if the particle was moving straight, then it will, have to go from here to India and back, again or something. So that's going to be ridiculous. How are we going to control the whole thing? So how will we do it, please? Yeah, what people use is something called a cyclotron or a synchrotron. These are basically what you do is you confine the particles, charged particles that you're trying to accelerate in circles by applying a magnetic field. So magnetic field is not going to change the velocity of the particle, the speed of the particle. It will only change its direction. Why will the direction be a good thing to change? Because then we don't have to send the electrons from here to India. It can just be, in this room rotating several times. As it keeps rotating, it will get faster and faster because we keep applying electric field to make it move faster and faster, right? But then we rotate it several times before it comes to the speed that we want. And what we are going to see, you can see that, like for example, in this particle physics facility called synchrotron, what they do is that they keep changing. As the particle keeps moving faster and faster, they also keep changing the magnetic field such that the radius stays constant. Do you see what I'm saying? So what they are doing in this facility, in particle physics experiment, for example, in synchrotron, you can see the word synchrotron means, suggests to you that something must be synchronized, right? And what they are synchronizing is the magnetic field, because you can see you want some charged particle to be moving, positive or negative, to be moving in a circle. And what are you doing over time? You keep applying. Every time the particle, say for example, comes at these locations, you apply an electric field to accelerate it, to make it move faster and faster. But if you are applying an electric field, to make it move faster and faster, as the speed increases, don't you have to increase B also? Because look, radius is equal to mv divided by qb. This is what we learned just now. So if the mass of the particle is fixed, if the charge of the particle is fixed, which it is, these two are fixed, if we increase the velocity, Shouldn't we be increasing the magnetic field if we want to keep the radius fixed in which it's moving? And that's the kind of thing that particle physicists have done in many places. They have these rings in which these charged particles are moving, and this kind of a facility is called a synchrotron facility, in which the particle moves several times and it keeps getting faster and faster because there's an electric field that makes it move faster and faster every time. But after several times, the speed becomes what you want. Okay, but you have to adjust the magnetic field. As the speed, if we want speed close to speed of light, we need a very high magnetic field also. 1 Tesla magnetic field is already very high. Producing 1 Tesla magnetic field, that's the kind of magnetic field you use in the MRI machine, and the MRI machines are costing more than $1,000 per scan, again due to the fact that producing a very high magnetic field is very difficult, because what you have to do is have wires that are carrying current which are very large, right, of the order of 1 ampere, and those kinds of currents are extremely large currents. What will they do? If you run them in a regular wire, remember, twinkle twinkle little star, power is equal to I square R, you are going to actually lose energy, so much energy in the form of heat, right? I square times R will be so large because the current is so high. Even if you're using copper wire and you can say, oh, this is a very low resistance wire, it doesn't matter. When the current is very high, I square times R will be still significant. Heating due to that I square R is going to be so large that the wire will melt down. That means if you want to pass 1 ampere current for a while in an MRI machine or in these particle accelerators, because what you have to do is you have to put some things to cool the wire down. You have to use superconducting wires. You have to use, because superconductors have no resistance, so there is not going to be any power dissipation, I square times R, so there's not going to be any heating produced. So you can safely run currents which are very high and hence produce magnetic fields that are very high. So again, in the MRI machine, you can hear this click, and you ask the operator, what is this sound? They'll say, oh, this is the helium chamber that is, cooling the wire down to reduce the resistance of the wire to 0, so that we don't have any heating, and same with the particle accelerator. And so I just want to tell you, these are some of the applications of magnetic field. So in this particle physics experiment, they're tilting the particle using the magnetic field. It's not being used to speed up the particle. They use a separate electric field to speed it up. Right? Any questions about this? Have you heard of this device called mass spectrometer? What do you think that is? And do you know how it uses magnetic field? Please.
It uses a magnetic field to bend the charged particle around in a flight tube, and then separates the particles based on mass.
Very good. So again, it's exactly the same principle that we are talking about here. Do you see that if suppose, so what will a mass spectrometer do? Suppose you have particles that have slightly different masses. Maybe they were isotopes of something, right? So one of them was carbon 12, one of them was carbon 13. If the two of them have a little bit different masses, what do you see? Do you think that even if they were moving at the same speed, even if they have the same charge, even if they are moving through the same magnetic field, if the mass is different, do you think their radii will be different? It will be, right? And so what you do in a mass spectrometer, for example, it can be used to separate particles which have different masses, but they may have exactly the same speed, for example. Or you could do the other way around also. If the masses are the same, you can separate particles that have different speeds, right? So, for example, it can be used to separate particles with different masses or speeds. So for example, what you would do is you would have a magnetic field and you launch these charged particles. Let's say that we launch these charged particles here. This is just charged particle that is launched, right, in this magnetic field. You can see that if I launch it like this, V cross B, okay, so in this case it seems that this particle will actually tilt like this, See, V cross B is pointing, my thumb is pointing this way. Do you see it will make a circle like this? What you can see is that depending, if suppose the speed of all the particles is the same, but the masses are say m1 and m2, they're suppose they're two particles, do you see that they'll actually move in two different circles? Do you see that the radii will be different? This is R1 and this could be R2. Right? Why? Because we are again talking the same thing. Suppose V is the same, Q is the same, they're going through the same magnetic field, mass is different, radius is different. Larger is the mass, larger is the radius, right? So R is equal to, R1 is equal to M1 V over QB, and R2 is equal to M2 V over QB. And since these particles go in circles of different radii, you can collect them at different places, right? So and this device is called a mass spectrometer. You can use it to separate particles of different masses. And again, you can see what the magnetic field is doing is it's bending the particles in circles of different radii. That makes it easy for you to collect particles with different masses that are moving at the same speed. Or if the masses are exactly the same, but the particles have different speed, you can still separate them, right? Any questions about this, folks? Anybody has any questions? No? All right, then the next thing that we are going to talk about, here is the thing. We talked about forces on charged particles in a magnetic field. We talked about the trajectory of charged particle in a magnetic field. What do you think will happen if I put a current carrying wire in an external magnetic field? What do you think? Because isn't current carrying wire moving charges also? Doesn't that have moving charges? You know, current carrying wire is nothing but moving electrons, right? What do you think will happen? Do you think it will feel a force? Yes, it will. So let's now talk about the force on current carrying wire in an external magnetic field. Okay, so for example, let's say we have a long straight current carrying wire like this, okay, very long, you can think of it as almost infinitely long, which is carrying current I up. Let's say it's placed in a magnetic field which is crosses. That means the external magnetic field is pointing into the board. Here is the thing. So this is the magnetic field crosses. The question is, what would be the magnetic force F sub B on this wire? Now, in order to find this magnetic force, all you have to do is conceptually realize that current is nothing but moving electrons. And then we are going to make use of the same equation that we used for moving charges. So we know that force on moving charges is this, Q V cross B. So the thing is, this is the force on a moving charge, and we know that current is nothing but moving charges. When I say current is flowing this way, really the electrons are flowing down, or you can, if you like, in your mind you can think that some positive charge is moving up, which is equivalent to electrons moving down, but in reality we know that positive charges don't move, right? It's the electrons that are moving down. Now, what happens if I divide and multiply this thing by t? Am I allowed to do that with some time t? I can do that. I can divide and multiply any expression by the same thing. It doesn't change anything. Let's say that, you know, we are talking about, suppose there was some electron E here, and then after some time this electron reached here, you know, and this is the time t in which the distance that the electron traveled is L. So the thing is, what will be V times t? Will V times t be the length L, but it will be a vector, so it will be like length vector if you like? Wouldn't you say that? Yes. So the thing is, and what is Q over T? Isn't that the current? Is Q over T the current? charge per unit time, remember that was the current. So basically what we find here is that F of B is equal to Q over T, which is the current, V times T, which is the length vector, we are now going to call it the length vector, times B external. And this is the expression for the force on a on a current carrying wire in an external magnetic field. You can see that it's a cross product of the length vector times length vector and the external magnetic field, right? Now here is the thing, as I said, maybe an easier way for you to think about this whole thing is just to say, oh, what I'm going to do is I'm going to think of this length vector. By the way, the length vector is a vector that is in the direction of current. Length vector is pointing in the direction of current. So the easiest thing here to do is to think that the direction in which the current is moving, there is some effective positive charge moving in that direction. Truly the electrons are moving down, but it effectively amounts to positive charges moving in the direction of current, right? So the point is that this vector L points in the direction current in a length L. Current itself is a scalar quantity, by the way. Current itself doesn't have direction, because the thing is, you know, when there's a current flowing in this wire, I don't say it's pointing south of west or north of east, you know. You can say it's flowing clockwise or counterclockwise, but that doesn't make something a vector. Vector means a specific direction. You have to be able to say it's pointing north of 30 degrees south of west or something like this. So now the question is, can we find the force on this wire? Again, you can see that the magnetic force should be perpendicular to L and to B, right? So in this particular case here, there are only two choices. What are the two choices? Huh? Well, I mean, if the current, if the length vector L is this way in the direction of current and magnetic field is cross, the force can be either this way perpendicular to both of these, or it can be this way perpendicular to both of these. The question is which of these it is. Use your right hand rule. Put your fingers in the direction of length vector, that means in the direction in which the current is flowing, cross it in the direction of magnetic field. Do you see my thumb is pointing this way? That means this is not the right direction, this is the direction of the magnetic force. Again, the magnitude of this force we can see that the magnitude of this force is going to be I L B times sine theta. Is that making sense, folks? Any questions about this? So if you, for example, tell me that the current in this wire is 0.1 ampere, if you tell me that the length you want for some length element which is 1 meter, the external magnetic field has a magnitude of, say, you know, 0.5 Tesla, which is very large, and the angle between the magnetic field and the length element is, let's say, 30 degrees, then we can see that the magnitude of magnetic force is going to be 0.1 meter times 0.1 ampere times 1 meter times 0.5 Tesla times sine 30 degrees, and sine 30 degrees is a half also. So this is basically 0.1 times 0.5 times 0.5 Newton, and the direction is given by over there, that thing. Any questions about this, anybody? Is this making sense? All right, so now let me give you a plausible explanation for why, if I have a wire loop, so now I don't have just a straight wire, but let's say current is flowing in a circle. in some kind of a loop. The thing is there a way for that loop to feel a torque due to an external magnetic field? Let's think about it. So I want to now discuss torque on a current loop in an external magnetic field. By the way, this discussion is very useful for making, for example, things like generators and motors. We will talk about them. Do you know what motors do? What do motors do? They convert electrical energy into mechanical energy. And what do generators do? They convert mechanical energy into electrical energy, right? So for example, in a hydroelectric power station, you must have a generator. What do they do? For example, in Niagara Falls, water falls from a big height, right? You can take advantage of this mechanical energy. It has a lot of kinetic, potential energy which gets converted to kinetic energy once the water comes down. If you can have a coil, current, if you can have a coil, and even if the coil is not carrying current, and you put that coil in a magnetic field, as the water falls, if this thing starts to rotate, what we will see, in a few days, is that a rotating coil in a magnetic field produces current. And that's how hydroelectric power is generated, near Niagara Falls, for example. Okay. Also, the reverse is true too. So, for example, if you connect a moving coil to power supply and you actually pass current through it, right, and it's sitting in a magnetic field, what you will see is that it feels a torque and it will start to rotate. So these are two opposite things. So if you supply it already some electricity, it will start to rotate, which you can use for something else. Or if it is sitting in a magnetic field but doesn't have any current in it, but you rotate it, you will generate current in it. That's the generator principle. So let's see possible reasons for why this might happen. We'll talk more about it next time, but let's just think about simply what's going on here. So let's say we have a coil here like this, okay? So, and let's say right now we are talking about something that already has current in it. So let's say this coil already has current in it. So we are talking about torque on a coil. In an external magnetic field. Okay, and here is the thing. So it may be a little hard for me to show what I'm trying to show here, but let's say that here is the magnetic field. Let's say there is north pole here, okay, south pole here, in which case the magnetic field is pointing this way, right? If this is north pole and this is south pole, the magnetic field lines outside the magnet go from north to south. Maybe this is a horseshoe magnet or something, all right? Suppose this is my coil. So this is one, there's nothing in between, but this is my wire in which there's current flowing. Suppose I hold it like this, right? What do you think will happen? First of all, is there any net force on this coil? Let's think about it, okay? So the magnetic field is pointing from the north of the horseshoe magnet to the south like this. So the magnetic field is this way. Let's say the current in the top part here is flowing towards you. The bottom part, it's flowing towards me because the current is like this, okay? So in the top part, if I use my right hand rule, this thing I L cross B, let's do it together. This is my right rule. I L is like this, right? Cross B, B is this way. Do you see the force is down like this? Right? Okay, what about in the bottom element? You can already see that in the bottom element, if the current is flowing this way, magnetic field is this way. Do you see the force is up? These two forces cancel each other out. So there won't be any net force due to that, right? Okay, in this element here, the current is down, right? The current here is down and the magnetic field is this way. Do you see the force is this way towards me? What about over here? The current is flowing up. If the current is flowing up, let me put my fingers like this, right? Magnetic field is that way. Do you see thumb is pointing that way? So again, the force in these two elements cancel each other out also. So in other words, a wire loop does not have any net force. So the thing is, first of all, net force, net magnetic force is 0. Is everybody convinced that it's 0 if it's a wire loop? Okay, but the question is there a torque on this? And the answer is yes. Why does this feel of torque? Huh? Can you think about why this thing might feel a torque? So let's say that we tilt it at a certain angle. Let's keep it like this, okay? Why would there be a torque? What is torque? Torque is? Anybody remembers what torque was? It's the analog of force in the rotational motion, right? So torque is equal to R cross F, remember? Do you remember that? So torque is a vector which is basically nothing but it's the moment of force. It's R cross F, right? So let's think about why there might be, I'm not going to do the full calculation, but the thing is, let's just think about why there would be a torque on this. And you can choose any point as the point about which you're trying to find the torque. Let's say we are looking at this point here, okay? What did we already say? We said, if you remember, what did we say? Which way was the force on, say that this thing, the top thing? If the current is flowing that way and if the magnetic field is there, is that way, do you see this cross this, the force is pointing down. Do you see that? Let's keep it a little tilted here. So is everybody with me right now? So I'm saying, let's say the current here is flowing this way. This thing is tilted slightly. So here we have current flowing like this. The magnetic field was pointing that way. So I cross B, the force is down here, this force. In this part, the current is this way, right? So if the current is that way, put your fingers like this, the magnetic field is pointing this way. Do you see the force is up? Do you see that now we are saying in this little part of the current, segment of the current, the force is up. In this part, the force is, the force is down here in this part because I cross B is pointing down and here I cross B is pointing up. Do you see that they form a, and so if I'm finding the torque about the center here, is there a torque? Yeah, torque is going to be F, R cross F and R cross F. And do you see that both of these are producing the torque in the same direction? Which direction are they producing the torque? Which way will this thing start to rotate? Very good, because the thing is you can see that here the current is flowing that way and the force is like this. Here the force is up. Do you see that? That it will start to rotate. So basically what we are saying, and this is the principle, this basically is the principle of what? Motor. This is the principle of motor, because what we are saying is that you give it electrical energy, you pass current through it. If it's sitting in a magnetic field like this, it will now have kinetic energy. It will start to rotate, right? So we are converting electrical energy into mechanical energy. This is the principle of motor. All right. Next time we'll talk about how to find the magnitude of this torque. All right. Have a great day, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.